Hello again. So it's me again. I'm going to. It's always tough to follow Guillaume with his beautiful slides. It makes all of us feel a little bit inferior. These are just standard old slides. So sorry, the pretty drawings are done for the day, I think. So what I'm going to talk about is something that we've built at Criteo in the space of big data, which is something we call data reliability engineering. It's not a tech talk. We're not going to talk about specific technical details. I'm going to gloss over lots of things. It's more trying to convince you that data engineering and systems engineering can go hand in hand and create something called data reliability engineering. So, right, so we're not going to be talking about how big our Hadoop cluster is. Thankfully, Guillaume did that earlier. And what we are going to talk about, like I just said, is the principles of data engineering combined with SRE, site reliability engineering. The specific, just one word on scale. So a lot of times we're going to talk about scale. We say, oh, scale's hard, scale changes everything, and that's all true. But it's also a good way to lose yourself in details, right? So we have a batch job that's 150 terabytes that we need to get scheduled immediately. How are we going to do that? Well, it's hard. You know, it needs you need to depend on quite a lot of solid systems at various levels in the stack, and when we're talking about that problem, we're going to be talking about the very, very specific problems that that sort of scale brings. But we lose ourselves in the details, and we're not thinking about the paradigm, which is what's more important. And so this, I don't want to, that's all I'm going to talk about scale for this presentation. So fundamentally, my thesis is data reliability engineering is what you get when you apply the principles of SRE to data engineering. Data engineering is a relatively new thing, but it is a thing, right? I think we can all agree on that. I think everybody's interested in this conference and other conferences of the same ilk, Spark Summit, Strata, all these different conferences that get thousands of people to show up. Not this one, but other ones. I think we can all agree that data engineering is a discipline in and of itself. And if we want to consider it from a systems perspective, then I think that data reliability engineering can be considered a discipline as well. And so that's kind of what I'm going to present for across the following slides. So a little bit of context, as a famous man once said, it's worth about approximately 80 IQ points. So the context is pretty quick. We started about 6 years ago on this problem. I think we had 2 engineers, 2 ICs, myself, and an analyst, and we just spun up a team to solve the BI problem at Criteo, and we called ourselves BI Engineering. It's also of note that 6 years ago is actually a long time in Hadoop years, right? So 6 years ago, Hadoop was still really immature. There was no reference architecture. Some shops, Twitter, I think, was starting to come out and talk about their architectures, but nobody really had, Gartner wasn't really worried too much about this space at that time. They were talking about it, but the MapReduce paper came out in 2004, but Hadoop 1.0, I think, was mid-2012, right? So that gives you an idea, and we were doing this mid-2012. So all we did was, we were, 4 people interested in the space, tasked with a mission, and so we just put our heads down and coded, not really knowing what we were doing. So as it turns out, we did build quite a few useful things at Criteo. We built petabyte scale data warehouse in Hive. We had a SQL Server database at some point for all the reporting needs, and we replaced that with this big fancy Vertica MPP columnar database. We built gigantic cascading jobs tackling tons and tons and tons of data. We were sort of the heroes. We had solved all kinds of problems. We retired a bunch of legacy systems that no longer scaled, and everything was great. Of course, as things went along, those things that we built, a couple, 3 years later, started failing. And as it turns out, a lot of them sort of started failing at approximately the same time. We built them all approximately the same time, and the scale kept coming, and at some point things started breaking down. And by the way, just to tie into Guillaume's talk, this is also when we started ramping up on the functional engineering stuff, when Scala started to become an important player in language choice. And so we were learning across multiple axes: data, functional programming, scaling teams. The team is going from 4 engineers to almost 40 now. So, lots and lots of things were happening. We didn't, despite the fact that things were breaking, we sort of accumulated our wisdom along the way, right? We didn't just sit back and academically consider, this big thing and said, oh, well, what are the learnings we can take from, failure A, B, C, D, and E, and success X, Y, Z, right? No, things were just sort of breaking and fixing and breaking and fixing, and and we just sort of accumulated little pieces of wisdom. The interesting thing is that large-scale distributed systems present in some senses they're very binary, right? So if you put something into production and it works, it doesn't break anything, that's sort of the formal proof that it's correct, right? And as you're seeing these things go in or get rejected very, very quickly, I mean, the cycle's really quickly. Like if you put a job into production, transforming 100 terabytes of data, if it's not coded right, you get immediate feedback, right? Your tasks start crashing. You have hugely skewed reducers. You have the name node breaking. You have immediate feedback, right? So you have to take that out of production. You have to look at it. You have to reconsider it, put it back into production, and hopefully very quickly get something right. And so this is sort of the binary nature of, at least that I've seen with large-scale distributed systems. And so that makes it a little bit easy to identify things that are working as well, right? If it's in production, it's working, basically. So on to the discipline of data engineering. So there's some of you may have read a blog post by a guy by the name of Maxime Beauchemin. For those who don't know who he is, he's the guy who wrote Apache Airflow and Apache Superset, and he wrote up a great Medium post called Functional Data Engineering. And he talks about he talks about a fair number of very important principles. DAGs, idempotence, replayability, and change management of data. And these are primary concerns of any data engineer, right? DAGs are, for those who were here yesterday, I gave probably 30-minute discussion about that one sentence, so I'm not going to go into much detail here. But DAGs are the graph of how your jobs are going to be orchestrated in their execution. Idempotence is that we can re-execute something without having anything fail. Replayability is the fact that we can safely replay any portion of that graph because it's idempotent. And change management is obviously we need to get new features into production, and sometimes we need to get new features into production not just going forward, but in the past, right? Because this is data, this is time series, and you want to have some body of data to look at to do analyses. So even Maxime has done quite a lot. So he knows perfectly well that scheduling semantics, which is basically what he talks about in functional data engineering, is just a tiny piece of the puzzle, right? In fact, before data engineering existed as a space, before Hadoop, and we had to worry about like the runtime and where you were deploying your stuff and how it was going to break in some new fancy way. People just cared about the content, the thing that was going across those that graph. These graphs have always existed. They've been orchestrated in the past by sort of off-the-shelf ETL tools that any sort of enterprise shop will sell you. Oracle has one, Microsoft has one, Pentaho is an open source version of these sorts of things, and they've existed for decades, right? And since those tools basically worked, right, the people were actually caring about the content. and the functional correctness of the content, right? Is the content, does it correspond to what the business needs? And believe me, somebody who understands what the content should look like from a technical perspective, having a conversation with a business person who says that I need, displays, I need to know how many displays, I need to know how much money we're making. These very, very high level business problems, translating that into a technical deliverable is non-trivial, right? It's an entire discipline just in and of itself, right? You have to be able to talk to business, you have to be able to understand the platform that you're executing on, you have to understand all the constraints, and squaring that stuff is really hard, but that's to my mind, that's sort of the principal job of a data engineer, is to do that, right? Because content is king, right? So now, right? So the platform, right? So data platforms. I am a huge user of Hadoop. Criteo is a huge user of Hadoop. I think any user of Hadoop will tell you that it's not the most enjoyable place to push production code to, right? There's a lot of things that are complicated all the way down, and you have to know about them. You can't not know about them. If you don't know about them, if you're operating at any sort of scale, when I say any sort of scale, the minute you've got maybe a couple dozen nodes in production, you're going to start running into some of the problems that underlie Hadoop, right? And principally one of those is distributed systems, right? You have to understand you're expressing some sort of data transformation. You're going to push that into production. You really do need to understand how it's going to be sliced and diced, and how that particular expression of data transformation is going to be executed. Because if it goes wrong, you need to know how to dig into those details and fix it. So that brings you to understanding MapReduce and Spark, columnar storage formats for efficient access of the data that you've been producing or that you need to consume. Relational database architecture is incredibly useful as well, because fundamentally, what is Hadoop? What is all this stuff? Well, it's a big, giant database, right? There's another thing that I think all data engineers should know, and all engineers should know, right? Is those numbers we should know in terms of access times in memory, in SSDs, on disk, and over the network, right? These are sorts of things that. These rules of thumb, if you keep them in your mind when you're having conversation with folks about is something possible, well, it allows you to sort of filter out the snake oil. And in this space, in the big data space, every week there's some new blog post that promises you that everything's going to be all right if you just use this, solution X. And if you've ever worked at scale in any place, and again, scale is always relative, right? So for Criteo scale might be unimaginable to some of you, but I guarantee you that Criteo scale, when it was an order of magnitude smaller, was still complicated for Criteo, right? It's always complicated, and these blog posts are, more trouble than they're worth in most cases. And so those numbers you should know are quite useful. So quick talk. So now, I've talked about data engineering principles, platforms, creating content, and things like that. A lot of folks will stop right there too. They'll say, oh, well, okay, my God, this is already really hard, right? Now you're going to ask me to do something else, like visualize the data? I don't care, like go talk to somebody else. But in fact, guess what? Reporting is the prototypical use case for any data warehouse, right? I mean, why are we building this data? So it can sit in a bunch of tables in a database? No, nobody cares about that. People care about getting that data out. And whether it's being rendered in charts or in a tabular format, it's still being rendered. It's still being processed and extracted and transformed and given to a human, right? Fundamentally, even if some data systems are built to feed other data systems, they all end up at some sort of human consumption point of consumption. And so the funny thing about data visualization is that it's really the same thing. So up till now, we've talked about how the fact that basically we're talking about data producers, right? Well, now we're talking about data consumers. People are going to consume the thing that you've been producing. Well, the tools that they're going to use to consume the thing that you've been producing are fairly similar to the tools you've been using to produce it, right? Certainly at Criteo, we produce a lot of data using SQL, right? We use Hive. Hawken's going to probably touch on the work we've been doing with Presto. And SQL is this great data transformation language. It's also a great language, of course, to extract information from data, which is fundamentally what you're doing when you're producing data, but in any case. So knowing the runtime complexity of queries is important because this is going to inform how you're going to structure the data so that those queries can be quick. And then when you start structuring the data, that's going to inform how you build the data pipeline, right? And how those queries are going to be running is also going to sort of inform maybe the low-level data format that you're going to be used for storing data in Hadoop. You know, does it need to be? Should it be columnar or should it not be columnar? There are use cases for both, and these are the sorts of things. So it's really important that as a data engineer, you're thinking about the visualization part of the problem, because a good data engineer is one of the best people to think about reporting problems. Okay, so I'm going to stop there in terms of what data engineering is. Notice I haven't said what it isn't, but I think hopefully you know, I've sort of convinced you that data engineering is a broad subject. So what is SRE? Well, so Google wrote a book, right? You can't click that here, but you know, when this slide becomes available, you can click it, or you can just look up Google SRE book, right? In Google, or DuckDuckGo if you know you don't like Google, but you still read their book. And so there's a lot of stuff. Despite Google's efforts at defining SRE, I think that SRE is up for interpretation. Mine is what I've written here. An SRE, so a site reliability engineer, is an expert coder automating the deployment and operation of her systems, evolving it via discussions around SLIs, SLOs, and SLAs. So for those who maybe haven't heard of SLIs and SLOs, SLIs are the indicators, SLOs are your objectives, and SLAs are what you agree to do when you've gone over your when you're out of your agreed upon objectives, right? So it's a way to formalize contracts with clients, basically, right? And so the more we can formalize a contract with our client, the more we can have more informed discussions about new features or capacity planning and budgets and things like that. And so this is a really critical way to look at engineering problems. All right, you guys all see, everybody's sitting, all right? So here's the big unveil. So what is data reliability engineer? She's an expert coder automating the deployment and operation of her data systems, evolving it via discussions around SLIs, SLOs, and SLAs. That's it. That's the whole deal. You know, it's a little anticlimactic, perhaps, but that's really it. So if we go back to my earlier statement that data engineering is a discipline, if you are following me there, and if you agree with the principle that SLIs, SLOs, and SLAs are excellent ways to have conversations with your clients about new features, including new fields that need to be propagated into different database systems, because sometimes those fields are very expensive to have traverse all that entire pipeline, then I think that we can all agree that data reliability engineering is up there with disciplines like site reliability engineering. And that's it. So thank you very much.